Hello everyone, my name is Sasut Rastamali. I am a researcher at the ACSL lab at Keio University, Japan. In this talk, I will be presenting our paper, Multi-Objective Reinforcement Learning for Energy Harvesting Wireless Sensor Nodes, which I co-authored with Professor Masaki Kondo and Professor Hiroshi Nakamura. Harvesting wireless sensor nodes are sensor nodes that harvest energy to operate, and they communicate wirelessly. This means that they're very portable and capable of working autonomously for very long periods of time. As a result, energy harvesting wireless sensor nodes have become very attractive as edge devices in the Internet of Things. Their numbers have scaled rapidly in the past few years and are already reaching billions. It is important for these sensor nodes to maintain energy neutrality. What this means is that their energy policies should be able to balance energy generation and consumption despite the uncertainty in the availability of harvestable energy. Traditionally, it was sufficient to maintain energy neutrality while optimizing for a single task such as sensing or communication. However, modern sensor nodes have become increasingly powerful and sophisticated. They execute different tasks such as sensing, communication, and processing, which consume significant energy. However, since all tasks extract energy from the same limited energy pool, it is necessary to allocate energy among the tasks intelligently. How the energy is distributed among tasks is determined by the user-defined relative priority, which is generally not known during the design phase and may change dynamically depending upon the operating conditions. Thus, we require a method for our energy harvesting nodes to first maintain long-term neutrality, second, intelligently distribute energy between tasks, and to fulfill the user's service requirements. To this end, we propose a multi-objective reinforcement learning framework to find solutions for this multi-objective energy scheduling problem. In our paper, we first formulate a multi-objective Markov decision process that is applicable to any general multitask energy harvesting system. We then propose two multi-objective reinforcement learning algorithms that derive near-optimal solutions while decreasing the learning and computation cost as much as possible. Our results show that our methods can learn near-optimal policies with very little learning penalties, and that with our methods it is possible to trade off between the utilities of different tasks at runtime as required by the user without any significant overhead. Let us now go into what reinforcement learning is. Reinforcement learning is a machine learning technique for sequential decision-making tasks. An agent, in this case this is our energy management module of the sensor node, looks at the current state of the environment. The state includes various information such as energy availability and task requirements. With this information in mind, the agent chooses to take an action. In this case, we assume it is the duty cycle of the node, which corresponds to the energy consumption of the node. And as a result of that action, the environment reacts to it by changing its state and provides feedback to the agent in the form of a single scalar reward. On the basis of this reward signal, the agent learns to choose more optimal actions so as to maximize its cumulative reward. As you can see, reinforcement learning is a trial and error learning process where the agent ideally learns progressively better policies with more experience. Normally, reinforcement learning's methods are for single objective. That means the reward signal that is generated by the environment is representative of one and only one objective. In our previous papers from 2007 to 2019, we used the energy neutral performance of the node as a reward to maintain energy neutral operation. What this means is that the agent learned through our reward signal to optimize the duty cycle such that the battery charge and discharge profiles over long periods of time stay within the safe green limits and avoids overflows and downtimes. Overflows are conditions in which the battery is fully charged and the excess harvested energy is wasted, which we do not want, and downtimes occur when the battery is completely depleted and the node stops working, which also we want to avoid. To overcome these limitations of single objective reinforcement learning methods when we need to deal with multitask energy harvesting wireless sensor nodes, we now go into multi-objective reinforcement learning. For multitask energy harvesting nodes, we propose a multi-objective reinforcement learning method where each task has its own well-defined independent reward signal. The agent uses these reward signals from all these different tasks to optimize the energy budgeting to maximize the node utility. The state space now also includes the relative task priority, which is given by the user. So ideally, we want the agent, the reinforcement learning agent, to generate more utility for tasks with higher priority, which usually means allocating that task more energy. The ultimate objective is to maximize the node utility, which is the sum of the different task utilities weighted by their respected priorities. We will now look into the difficulties of learning a policy that can optimize and trade off from different tasks by learning via multiple reward signals. As mentioned earlier, traditional reinforcement learnings cannot be used when there are many sources of conflicting rewards. However, one workaround is through reward scalarization, which means some linear nonlinear combination of multiple rewards into one scalar. For example, in the 2018 paper, the authors multiplied different reward signals and developed energy neutral policies. However, these policies were not optimal because the actual objective was well defined due to the noisy interference of the different reward components. In another paper, the authors used a weighted sum of different rewards. However, major limitation of this method is that the relative weights between the different reward components need to be decided and fixed beforehand. Any change in relative weights would require the agent to start relearning from scratch, and therefore this method is not very flexible. There are other scalarization methods too, but they result in very complicated reward functions that are not well defined and may result in non-optimal policies and unexpected behavior. So, to overcome these limitations of scalarization methods, we proposed our multi-objective reinforcement learning framework, which consists of two parts. The first part is the multi-objective Markov decision process formulation, which includes the multiple reward scenario and continuous state action spaces. Our work is the first one to include continuous states and actions, whereas previous works usually dealt with discrete states and actions. And as a result of the continuous states and actions in our formulation, we could learn more efficiently. And the second part of our framework consists of two multi-objective reinforcement learning algorithms that to learn trade-off policies. This is based on the deep deterministic policy gradient, or DDPG algorithm. The first algorithm is called the Runtime MORL, which uses pre-learned single objective RL agents, each optimized for a different task though, to dynamically trade off between different objectives as required by the user at runtime. The second algorithm, called the off-policy MORL, is used to simultaneously learn multiple optimizing policies for different objectives from a single experience stream starting from scratch using off-policy reinforcement learning. We evaluate our framework via simulations. We simulate a realistic sensor node that is powered by a battery and harvests solar energy. We assume that the user requires that the sensor is always on and therefore needs the battery to be above some minimum threshold at all times, otherwise downtimes occur. On the other hand, sensing and communication modules consume significant amounts of energy depending upon their respective duty cycles. From our experiments, we observed that the nodes were able to maintain near optimal energy neutrality using our framework. More importantly, they were also able to maximize the node utility by trading off the energy between different objectives depending upon what the user required. And moreover, the nodes were able to learn these trade-off policies with very little learning costs. I will focus mainly on the dynamic runtime trade-offs, or how our nodes were able to trade off between different objectives, in the next slides. So what were the different objectives that our sensor node had to optimize for? First, the node needs to regulate its energy for long-term energy neutrality. It learns to do this via the reward function shown in green to the right. The moving average of the residual battery level is a very good metric to determine the energy neutral performance of the node. So we use this to define our reward function. So as long as the moving average battery level is above a certain threshold, in this case this is 80%, the agent receives high rewards, and as this mean battery decreases, the reward is decreased linearly. If there's a downtime, the reward is zero. So this is the energy neutral objective. The other objectives have to do with sensing and transmission. So usually the utility of a sensing task is linearly related to its sensing interval or sensing duty cycle. So the sensing utility reward can be represented as a linear function of the duty cycles shown by the blue line. However, the same cannot be said for transmission tasks. the bit error rate decreases logarithmically with increasing transmission power. Thus, the transmission utility extracted has diminishing returns or a concave relationship to the transmission duty cycle. Our node has to optimize the duty cycles of sensing and transmission to maximize the node utility depending on the user's requirements while ensuring long-term operation. So basically, at each time step, the node receives a request from the user requesting sensor data at a specific sensing rate. The node then has to decide the energy budget for sensing, that is, to what degree it can satisfy the user's request, and determine how much energy to spend in transmission depending upon the channel conditions. This decision is made based on the user-defined relative priority between the sensing utility, transmission utility, and the long-term energy neutrality of the node. To measure the long-term energy neutrality, we look at the number of downtimes the node commits. If the node is perfectly energy neutral, there should be no downtimes. So lower downtimes usually indicate more energy neutral policies. So let's look at the results now. We're looking at the utility profiles and the downtime profiles for an off-policy agent, off-policy MORL agent, which needs to trade off between sensing, transmission, and energy neutrality. It shows the profiles from the years from 2005 to 2014 after it has been sufficiently trained. I want to bring your attention to how the sensing utility changes with the change in the sense priority, or omega sense. As the sensing priority increases, the MORL is able to optimize its duty cycle so as to maximize its sensing utility correspondingly. So as you can see, omega sense changes from 0.1 to 0.2, 0.2 to 0.7. So depending upon the different user priorities for omega sense, the corresponding sensing utilities also increase correspondingly. On the other hand, if you look at how the agent deals with different priorities for energy neutrality, we observe that when energy neutrality is given lower priority, as shown in red, the downtimes increase. And when energy neutrality is given higher priority, the downtimes decrease, which shows that our agent is able to optimize its policy depending upon what the user required. From the figure, we can also observe how our agent is able to trade off between the objectives of maximizing sensing rate and maintaining energy neutrality depending upon what the user is asking. This is achieved at a very low overhead with very little computation. Higher sensing utility will drive the duty cycles higher at the cost of lower energy neutrality, which may result in higher downtimes. Similarly, or alternatively, higher priority for energy neutrality will decrease the downtimes, but also correspondingly decrease the sensing utility. Hence, we can see that our MORL agent is able to successfully trade off between these two objectives depending upon the user's requirement. Of course, there are more results in the paper, so please be sure to go through them if you're interested, but I will stop about the results for now. So in conclusion, energy harvesting wireless sensor nodes require reinforcement learning for adaptive and scalable policies. It is difficult for using RL for multiple objectives due to how the problem is defined, and traditional methods do not scale well and have high learning costs and have very complicated functions, and you cannot do trade-offs. So we propose our framework to overcome these limitations, and we show that we can learn near optimal policies with very low learning costs and be able to trade off at runtime. And with this, I will end my presentation. I would like to thank my co-authors, Professor Masaki Kondo and Professor Hiroshi Nakamura, as well as GST Crest and GSPS for funding this research. Thank you very much.